Okay, you guys are ready? Okay, so today I want to talk about a couple of famous scientists who discovered some relationships. Actually, I'll leave the door open. Nick and Tony will be here soon. A couple of famous scientists who discovered some relationships that were really applicable to gases. Okay? The first guy, his name was Robert Boyle, and so we're going to attribute this first law to him. We call it Boyle's law. Okay? Here's what he discovered, that the pressure of a gas times by the volume of that gas always seem to be equal to the same number. And so with it being the same number, we call that number a constant, and that number, we use the letter K to represent that. Okay? I think I got a diagram here that can help show this. Okay? Hopefully this kind of makes intuitive sense. Let's say that you have like a syringe, some sort of like airtight container, and that container has a certain amount of volume in it. Okay? Well, there's going to be a certain amount of pressure inside the syringe. Why is there pressure inside the syringe, actually? Where's the pressure coming from? Okay, well,
the air
what's
coming down from the outside?
Sure. But like, let's say there's pressure even just inside the syringe trying to push back up. That's because there's all sorts of gases inside here, right? And what's happening to these gases? Well, they're moving, right? And in the fact that they're moving, they're going to hit stuff. That guy's going to hit there, that guy's going to hit there. They're going to move. Why do they move? Because they have what's called translational motion. You guys remember that term from yesterday? Vibrational, rotational, translational. These gas particles, they can bounce wherever the heck they want, right? And in doing so, they're going to hit the side walls of the container. Well, if they hit the side walls of the container, hitting would be like a push. And a definition for a push is like a force. You guys remember how like a force is a push or a pull? So these particles inside here are going to move with a force. They're going to move. It's going to cause a force. Well, a force is part of pressure because a pressure is really equal to a force over an area. And so as these things are inside here, there is an internal pressure. Does that make sense? Everything like this will have an internal pressure. Like my water bottle right here, as long as the air is all stuck inside here, there is a pressure pushing out on the edges. It's not really that much, obviously, but there is some pressure, right? Imagine a balloon. So you go, tie the balloon thing, right? Why does the balloon stay inflated? Why does the balloon not just, collapse back in a heap? Well, because again, you've got all these molecules inside the balloon that are pinging off the walls everywhere, right? And all of that pressure is keeping the balloon inflated. Key word, inflated, from the inside, right? Inside this balloon is pushing outward, keeping it from collapsing in on itself. Does that make sense? This principle applies to everything. Tires, footballs, basketballs, volleyballs, anything that basically is inflated. So, this diagram is going to be a little bit less misleading then. What happens if you were then to use an outward pressure and try to force it in? So like imagine you've got a balloon and you try to take the balloon and you try to squish it in further and further, like in this diagram right here. Well, what's going to happen is that if you increase the pressure, the volume would have to get smaller, wouldn't it? Right? Like if you on the outside apply a whole bunch of pressure, I mean it could be on all sides, but I mean in this example here they're just saying, well, what if you just increase the pressure right here? Forcing that stuff together, wouldn't logic dictate that the volume would have to get smaller? Now that's a little different though. Let's say I put some pressure onto this book. I am clearly pushing on this book. Is its volume getting smaller? No. Why? Well, these particles right here, what sort of motion can they undertake? Just vibrational, actually. They don't really have the ability to translate or to rotate, right? But gases, we can take gases and compress them and squish them in. That makes sense? So Boyle was the first one who kind of discovered this, or at least we attribute it to him. He said basically if you keep the temperature the same, and if you keep the number of moles the same, so like the amount, the volume is inversely proportional to the pressure. A couple of you guys are in my physics class. How do you draw an inverse graph? What does it look like? Remember? Yeah, it kind of looks like this. This is an inverse relationship, where this could be pressure and this could be volume. As the volume goes up, what happens to the pressure? It goes down. Yeah. I think I taught almost all of you guys math. We've done this graph before. This is the graph of like y equals 1 over x. We call it a reciprocal. So you could actually make a graph of this. You could say that V equals 1 over P. Your volume and your pressure are like inversely, like oppositely directed. If one goes up, the other has to go down. Let's say that you were to have a whole bunch of gas in a really highly pressurized container, but then you open the nozzle on the container and the gas escapes. Does it have as much pressure? I'd say no. Why? Well, as the volume increases, the pressure must then decrease. Makes sense? So we attribute that to Boyle. I got a picture here, maybe kind of a similar kind of concept. I'll just move on. So here's another law I need you guys to write down for like math relationships. Put this in your data booklet or your formula booklet. What do we call that? Your data book. Okay. Make sure you throw this formula in here. Basically, we've discovered that if pressure times a volume equals a constant, well, that constant could happen because of a second pressure and a second volume. So we have a formula I need you to know. It's called Boyle's Law. P1V1 equals P2V2. Let me see that this diagram here can help make sense of it. Right here, we have some molecules inside the container, and they're pinging around inside the container, causing some pressure. Why are they causing pressure? Well, they're moving. Because they're moving, they're going to hit the walls. Because they're going to hit the walls, that's a force. And force is basically related to pressure. Right? The more force you have, the more pressure you have. So there is currently some pressure inside here. What would happen if I took this volume of 1 liter and I squished it down and made it half a liter? Well, do we have any more molecules inside? No, there's still 1, 2, 3, 4, 5. So there's still 1, 2, 3, 4, 5. So we don't have more molecules. Are they moving faster? Actually, they're not. They're not moving faster. But the area with which they have to move in is so much smaller that they're going to hit the sides of the containers more often. Let me give you a different analogy. Right now, we have about 20 kids in this room. There's a lot of room for you guys to work, right? Are any of you guys currently bumping into each other? I mean, maybe if you're really vigorous with your writing, you need a lot of elbow space, but currently you're not really bumping into each other. Okay. But let's say we pack this room with 300 kids. Would there be more pressure then? Okay, now that's not fair though, because in this example here, I wasn't allowed to have more kids. So let's do this differently. Let's take all 20 of us and go into that office there. There's still 20 of us, but now are we going to be bumping into each other? We're not moving faster, but because there's less room, there's going to be more collisions. There's going to be more force applying because of less room. So here, when the volume went down, the pressure has to go up. That makes sense? Let's do an example. Let's say you have a gas that's 100 milliliters and 150 kPas. And then afterwards, we're going to increase the pressure. What should happen to the volume? So does volume go up or down? Yeah, we're gonna have to make it smaller, right? Okay, so let's try the math. V1, what is it? P1 V1 equals P2 V2. By the way, is this formula kind of familiar to the dilution formula we just did last unit? So your initial pressure is 150 kPas. Your initial volume is 100 milliliters. When you were done, your pressure was 200 kPas. And we just don't know what your final, I should use a V there. We don't know what your final volume is. There you go. So how do you get your volume by itself? Divide by 200. In terms of units, the kPas cancels. So you guys said 75 is the answer. 75 watts though. I mean, we're not in math. I need a unit. So milliliters. One more thing that's actually not right.
Because you started with 100, so you actually have 25.
No, it's the point zero you're missing actually. It's sig digs. Sorry, you're wrong there. It's about sig digs. This has 3 sig digs, this has 3 sig digs, this has 3 sig digs. So if you just said 75, you're only showing 2 sig digs. But if you throw a 0.0 on the end, now you have 3 sig digs. Does that make sense? Does it matter what the units of pressure are? The answer to that question is actually no, it doesn't. Do you guys remember the 3 main units of pressure we learned yesterday? One is KPA. KPA. mmHg, millimeters of mercury is another one. And someone said the last one, atmospheres. These are the 3 main units of pressure. Okay. It does not matter which units you use, except they have to be the same as each other. Okay. For example, if this was in kilopascals, but this was in atmospheres, we can't do that. You guys heard the phrase like you have to compare apples to apples and oranges to oranges. You can't compare apples to oranges. Okay. Whatever this unit is right here has to be the same as this unit. So if they're not the same as each other, you have to convert. But if they were both in millimeters of mercury, we'd have been fine. Let's try another example. You've got gas that is 350 kilopascals. So that's actually quite a bit of pressure. And it's in an 800 milliliter container. Let's say we drop the container's size. What should happen to the pressure, up or down? Yeah, we're compressing this in. So there's not more stuff in there. It's not moving faster, but it's just, there's not a lot of room. So again, this is like us shoving everybody in this classroom into the closet there. It's gonna be tight. That makes sense. So P1 V1 equals P2 V2. Our first pressure was 350 kPas. Our first volume was 800 milliliters. By the way, quick reminder, please write down units. I'm usually pretty big on being a stickler for units. We want to find our second pressure, and our second volume is 250 milliliters. Anybody get an answer? Hey.
I'm not sure if it's this class or your previous class, but there seems to be hundreds of pages of notes that have been sent.
Goodness.
And they're coming out in such huge volume, they're jamming the machine and nobody else can use it. So if people have in, I don't know if it is this class or whatever, but you guys need
What are
not
the notes
print
on?
again and again and again.
Same thing, guys. Stop printing notes 2 minutes before class, okay? Because, I mean, it's the same thing. You're jamming up the printer for everybody else who needs it. That's why I have notes on there.
Now it's gonna take some maintenance.
Yeah.
And I have a class too.
So, same thing, guys. Print your notes sometime else. Anybody get an answer? 1120? So that's KPA? Okay, so there's a couple of ways we could work with this 1120. You could go 1.12 times 10 to the 3 kPa. Here's another way of doing it. You know how a kilopascal is like 1,000 pascals? The next unit up is a mega something. So you could call this 1.12 mega pascals. Does that make sense? Either of these 2 ways would be a valid way of writing that. So hopefully that makes sense. I mean, as we squish the volume in, the pressure is now much bigger. Much, much bigger. Does that work? Alright. Why don't you guys try this one? See if you can do it without me doing it first. Yeah. It just means your answer will be in liters then. No, I mean you can convert your answer into something else then, right? Alright, so P1 V1 equals P2 V2. Basically, you just got to put all the numbers in the right spots. So, should have 400 kPas, 10 liters, 1350 kPas, and a new volume. Before we actually do the math, should we need more volume or less volume? Way less, because we're trying to increase the pressure, right? So how do you increase the pressure? Well, you squish everything in, right? If it used to take up this much space, and now it takes up this much space, there should be lots more pressure now. So we should have a much smaller container for volume. Again, I really want to point out, focus on making sure you write in your units, because you see how the kPAs cancel? Anyone get an answer? 3.0? Now, again, the reason why I want to point out the units, though, is since liters was the number that was left over, that's your units, right? If it had been in milliliters, then you'd have milliliters left over. One of the reasons I want to point this out is it does not matter what units you work with. It could be milliliters, it could be liters, it could be ounces, it could be PSI. You guys ever heard of PSI for pressure? Sure, it could be atmospheres, it could be millimeters of mercury. It does not matter so long as you know how to cancel units. So. Okay, second law. Second guy here, Jacques Charles, he was working on the relationship between temperature and volume. Okay. You guys have seen like hot air balloons before, right? How in the world do you get a hot air balloon to make someone be able to like rise up above the clouds? Well, it really has to do with temperature. If you heat gas, you guys have probably seen this before, when you heat gas, it expands, right? Hotter things are moving faster. Because they're moving faster, they're going to ping off of each other, so it's going to cause things to try to expand. And so really what ends up happening then is that this big balloon right here is full of really hot gas molecules bouncing everywhere, and it's actually lighter than the surrounding air, so there it's able to float. It has to do with like densities of air. Here's another diagram, maybe referencing the same thing. Let's say that you have this container right here, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules. Afterwards, there's still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So like I can't add more molecules, obviously, right? But these guys right here were moving, but then we heat them up. What happens when you heat up molecules? Well, they move faster. Yeah, they have way more energy. So if this guy used to move like with a little arrow, these guys now are moving with a big arrow. Okay. Well, if possible, what's going to happen is they're going to need more room, and so they're going to expand that container. Maybe you've seen this before with like say a balloon. If you take a balloon and put it into the fridge, it actually like it shrinks. But then if you take it back out and put it outside in the heat, it'll actually expand again. Maybe just another diagram here. Say you have all of these molecules at minus 65 degrees Celsius. They don't need a lot of room. But heat them up to 250 Celsius, and all of a sudden, they're going to need a lot of room because they're moving everywhere. So, here's what Charles did. He ended up doing a whole bunch of experimentation, and he plotted some information on a graph. He figured out how much volume things required at different temperatures, and he made a graph that looked like this. He had 5 points on the graph. Well, he then drew a line, like you guys might do in a graph where you draw a line of best fit through these points. But he decided, well, what if we keep going into the negatives? Because, I mean, clearly 0 degrees Celsius is not the lowest temperature possible. His idea was, well, let's see whether we can figure out the lowest possible temperature there ever possibly could be. And he just made the line keep going backwards. And eventually, when it got back down to like where this was 0, so like this is temperature, and this is volume. When the volume hypothetically would be 0, he figured out a temperature. And this temperature is 273.15 in the negatives. Anybody know what that temperature is called?
Kelvin.
That's what it's called, actually. Absolute 0, yeah. I like that you're trying.
When you say Kelvin?
Yeah.
It's not possible.
So absolute zero is considered to be the lowest hypothetical temperature that we could ever achieve. And we can't go lower than that value. Because at absolute zero, in theory, there would be no energy whatsoever. Molecules would be completely stationary. You guys remember how I talked about translational, vibrational, rotational motion? At absolute zero, there would be no motion whatsoever. Solid objects would not even vibrate. Now, one thing about absolute zero is that, as far as we know, it's completely hypothetical. We've never actually gotten an object to be exactly at minus 273.15. We've gotten it close, but we've never actually gotten an object so cold that it actually is completely motionless. Now, Sean, you shouted out kelvins. You're not right, but there's a different scale we use. Rather than using Celsius, this has been denoted as 0 Kelvin, which basically means that 0 Kelvin is the lowest temperature we can get to, and everything else goes up from there. So if 273.15 Celsius is 0 Kelvin, what does that mean 0 Celsius is? Anybody know? Yes, exactly. So if 0 Kelvin is this in degrees Celsius, then 0 degrees Celsius is actually 273.15 kelvins. So you guys know how there's degrees Celsius and degrees Fahrenheit? Well, there's actually a third scale that we work with, which is the Kelvin scale. If something is like, say, 25 degrees Celsius, it's almost 300 kelvins. So one thing I'm going to need you guys to be able to do is convert between kelvins and Celsius. So I don't think I have a formula in your notes here. So why don't we write the formula in? Degrees Celsius is going to be equal to kelvins if you subtract 273.15. And kelvins will be equal to degrees Celsius if you add 273.15. Sorry, I made a mess of that. Let me fix it. Does that make sense, by the way? So you're either adding or subtracting 273.15. Most of the time, though, we just omit the 0.15, and we either add or subtract 273. So if you want to skip the 0.15, we often skip that part.
0.15.
Yeah. Let's do an example. Convert 35 degrees Celsius to Kelvin. Let me try that. What would 35 degrees Celsius be in Kelvin? Do you add or subtract?
-6.
Well, we need this formula here because we want Kelvin.
Oh.
So 35 degrees Celsius is going to be a lot of kelvins. It's going to be 35 plus 273. So 308. Okay. A couple notes about kelvins. We actually don't use the little degree symbol. We just put K afterwards. So you're just going to say 308 K. Don't put the little degree symbol there. We actually don't use that in kelvins. What was that? What do you mean? Oh, yeah. Small K, big K. Small K versus big K. Let's do one more here. Let's try converting 47 Kelvin into degrees Celsius.
Wait, Kelvin's a big K.
Kelvin is a big K, yeah, sorry. K for Kelvin is a capital K. Is 47 Kelvin a lot? No, it's actually very cold. So in terms of formulas here, if you want to convert Kelvin into Celsius, we got to subtract. So 47 Kelvin minus 273. What'd you get? 226? Can someone grab that back door too? Thank you. Thank you. Does that make sense? So 47 minus 273? Negative 226? Okay. So we need to be able to convert between two different units of measurement for one major reason. We need to be in Kelvin. And there's a couple of big reasons why. The first main reason is we need a scale that actually starts at 0. It's kind of unfair to have a Celsius scale that just arbitrarily starts at negative 273.15. Anybody know why we use the Celsius scale anyways? Like, what's the uses to the Celsius scale?
Because when water freezes, it boils.
Yeah, that's why we developed the Celsius scale. It's based on water. Water freezes at 0 and boils at 100. But based on those units of measurement, then the lowest temperature possible is just this random negative 273.15, which is kind of an odd number to pick, right? So really the Kelvin scale is the best value because it starts at 0. Is it really reasonable to have a negative temperature? Well, I mean, in Canada, we think of negative temperatures all the time because we think, well, it's cold outside. Cold means negative. But, I mean, is there still heat outside even in the middle of winter? Sure, objects are still moving. So is it really logical to say that things can have like negative energy to them? I'd say, well, no. It's just we arbitrarily chose 0, like to be above it is like hot and below it is cold, right? But really, it doesn't really make sense to have negative numbers. Because can you have a negative pressure? Can you have a negative volume? Can you weigh negative mass? If you're trying to lose weight, that'd be awesome if you could somehow just have a negative mass, right? So why would it make sense that we should have negative temperature? Right? Well, the Celsius scale, like I said, the Celsius scale does involve negative numbers, but maybe it wasn't the best choice. I said this to my physics class a while ago. Sometimes in science we develop things, they catch on, and then years later we realize that maybe we shouldn't have, because like there's some flaws to it. And I think Celsius is a good example of that, because you can't have negative temperature. Does that make sense? So here's what I need you to do then. Every time we use a formula, you need to use a Kelvin number. So if I give you numbers in Celsius, you always have to convert them. Because here's the formula for Charles' law. Charles discovered that volume and temperature, they have a direct relationship. I have the wrong word here. This is supposed to be a direct relationship. If the volume goes up, the temperature must have gone up. If the temperature goes down, the volume goes down. So when you plot these, it actually is a nice straight line, which we learned in math is a linear relationship. Does that make sense? So volume and pressure actually have an inverse or reciprocal relationship, because if one goes up, the other must go down. But volume and temperature actually have a direct relationship. If one goes up, the other one also goes up, actually. So, let's try a question. Let's say you have a gas that's at 25 degrees Celsius and takes 22 liters, and then you heat it up. What's going to happen to the volume? Bigger or smaller?
Bigger.
Bigger, yeah. We're going to need a lot more volume because why? Well, these molecules are now moving faster. They're bumping off of each other all the time. It would be like, in this classroom right here, we have 20 of you, but then I feed you all energy drinks, and you're all buzzing off the walls. Do you really want to be confined in the classroom anymore? No, I'm going to send you outside and tell you to go play in the field. Right? And I'm going to need to increase the volume so you have more room to work with. So, our formula is volume over temperature is equal to a second volume over a second temperature. Don't do this though. You can't go 22 liters over 25 degrees Celsius equals V2 over 150 degrees Celsius. Why is that wrong? Have to convert everything to Kelvin. So make sure you try to get in the mindset right off the bat. When I talk to you guys about using units, this is one of the big reasons why. The units of Celsius is not the right units to use. So it actually has to be 22 liters over, I think this is 298 Kelvin.
You not want to split the decimal?
You can skip the 0.15. We typically skip the 0.15. 150 plus 273. What's that going to be? 423. Perfect. So K. So make sure that you convert Celsius to kelvins. So now it's more of a math problem than anything. How do you get this V2 by itself? Yeah. Yeah, I mean, you can use the term cross multiply if you like. That's applicable here. This 423 has to come up top there. So in terms of showing your work, it's now 22 liters times by 423 Kelvin, divide by 298 Kelvin, and now your V2 is by itself. What should happen with your units? Yeah, the kelvins cancel, right? So now I just need someone who has a calculator to help me out here. Say that again? 4,991.
I got 31.22. Yeah, I got 31.
Yeah, I got 31.
Okay, 31. Are there some decimal places afterwards?
0.228.
Okay, so let's just write those down for now. 31.228. What are the units for this then? Okay, liters. One last thing though, we got to make sure we round this properly. So in terms of sig digs, this had 2 sig digs. These ones right here each had 3. Now here's where sig digs get really screwed up actually. This right here appears to only have 2 sig digs, but it doesn't. It actually has 3 because as a Kelvin value, 25 degrees Celsius was actually the 298 Kelvin. So temperature values you got to be really careful for. Let's say I gave you 7 degrees Celsius. You might think 7, 1 digit, 1 sig dig. It's not true. It actually has 3 because 7 degrees Celsius in Kelvin is like 280. Does that make sense? So that being said though, the 22 liters is what's limiting us here. So we only do get 2 sig digs. So it's 31 liters. I'll write that again, that was pretty ugly. 31 liters. Does that make sense? Okay, well, I've given you guys a couple of formulas. Why don't you guys try these next 6 questions, see whether you can get them right. Do you guys have this slide in your notes?
Yep.
Okay. This is our last slide, right? Okay. Okay. Well, how about after this, if you guys finish these 6 questions, go take a break. And then after these 6 questions are done, we'll go over them as a group just to make sure you have them all right. So work on this when you're done that.